And our next topic is going to be focused on building a standardized data pipeline from the cloud to all devices in the vehicle. And with that, I would like to introduce our two next speakers, Mark Singer and Shivanji Baka from eSync Alliance.
Chris, I think you're a little off there. That's the next session.
Oh, I'm sorry. Excuse me. I'm sorry. Excuse me. Apologies. Sorry. Solving. Excuse me. I apologize. Solving data storage challenges in the automotive architecture, and Tom Dunholm from Texera. Apologies, Tom.
Not a problem at all. Thank you. Hello. Welcome today. So, what are the data storage challenges? Let's start by looking at a car. Pictured here, there are a lot of electronic control units. Some vehicle designs had over 100. Most have a microcontroller or a microprocessor, memory for some random access or storage, and other components. For those that were sophisticated enough to have operating systems, there were 6 to 8 different options represented vehicle-wide. Most of these ECUs were flashed once with minor updates over the life of the vehicle. They had a fixed use case, essentially a read-only system. Those that did write data, log files for instance, had that factored into their design. Lifetime of the media was not a concern. To better understand lifetime, I want to give a very brief overview of flash memory, and then we'll get back to system trends and the associated effects, especially where there are challenges for data integrity and lifetime. Flash media is used in most of those ECUs, as well as storage you're familiar with, such as USB, SD, and SSDs. It has a long history. It started with NOR flash, which evolved from EPROMs. This type of media has very fast read times, although not quite as fast as DRAM could be. Code could be executed in place from that media, very useful for system startup, and still used today. Unfortunately, writing and erasing that memory is very slow, not at all like a hard drive. So NAND came along. It was a bit slower to read, but much faster write and erase times. This was also available in higher densities, and so we started using a factor called cost per bit when we talked about it. Of course, NAND needs to be managed properly, so this is one more factor I want to touch on. Managed flash media like eMMC, UFS, SD, SSD has some firmware to handle wear leveling and bad blocks. These devices also contain a RAM cache, a microcontroller, and a lot more. That, of course, can drive the cost up. The other option is to use raw NAND flash chips and controllers, and then supply software to handle the wear leveling and the bad blocks. Linux would be one example of software that does that through what's known as a flash file system. The first NAND that came out was SLC, or single level cell. The NAND controller measures the charge on a cell and determines if it's a 1 or a 0, storing a single bit of information. One way to reduce the cost of the NAND is by storing more bits per cell, but that has a downside that we'll touch on soon. Still, this is a clever design. Measure the charge at 4 different places to store 2 bits on what was known as multi-level cell, or MLC. After that came TLC, 3 bits per cell, and QLC, where 16 different charge levels can be used to store 4 bits. Any confusion in that charge measurement, anything that's right at the threshold, can cause what's known as a bit error. And the NAND firmware or the software needs to correct that at read time, ideally then rewriting the data on the media to refresh that charge. That rewrite causes some lifetime problems, reducing the maximum program and erase cycles for the memory. Here we show the number of bits per cell and the declining cost, which is good, but unfortunately as the cost goes down, so does the endurance, as the overall number of program and erase cycles shrinks. Let's step back and think about that just for a second. 1,000 write cycles. How does my desktop SSD survive that? Well, if the drive is large, things aren't that bad. On a 1 terabyte drive using, let's say, a 500 lifecycle QLC and perfect wear leveling, you would need to write about 500 terabytes to that drive to exhaust the lifetime. The bit correction that I mentioned cuts into that total, of course, along with another factor known as write amplification. We'll get back to that shortly. So back to our vehicle with lots of ECUs. We talked about how most of them are flashed once. They're really a predefined use case. Some had NOR, some a little bit of NAND, but flash write really wasn't an issue. We didn't talk about the cost much. It's fairly high, and that cost has grown along with sophistication of the design. The vehicle has a moderate complexity, and the scope was well defined. Reducing the cost of components involves combining some functionality, consolidating the ECUs into certain domain controllers: cockpit, safety, body, chassis. Several functions captured in a single controller using hypervisor technology. Each hypervisor runs 1 to 4 guest real-time operating systems. Vendors provide separate partitions by function, and of course share the memory updates, so flash write is an issue. More on those challenges soon. These designs are always online, utilizing over-the-air updates. Each of those can reduce lifetime. Android's gaining traction in the newer systems, bringing new ideas and new apps. One example of these is monetization of new apps after the initial sale, which is a whole new business model. As you can see, this is a much more open system with a very high complexity, and it's not that easy to define and enforce design rules. So let's investigate a couple of challenges. One is the lifetime of the system. What's going to run 5 years from now? How will it interact? There'll be new apps and new updates. These also result in a much greater write load for the flash. A DVR or an event data recorder will need to store a lot of information, although only the last few minutes is crucial. The designer of the system can choose to overwrite the older data, but this increases the wear. Every single app, by definition, tries to log data also. This is in order to debug the system. Some of this is even mandated by safety standards. Customers can see a performance drop due to this additional load. Even if it's balanced properly, it's still quite heavy. Achieving 10 to 15 years lifetime for the system requires balance. A larger media part, or one with more write cycles, could be used, but then the cost goes up. Using MLC NAND can help keep the cost down, but then the write cycles shrink. One example where this was a reality is Tesla from late last year. The main control unit died on the Model S after about 4 years. Examinations found there was a greater than expected log data. Okay, so a lot more writes than expected. Tesla got out of this by saying it was out of warranty and asked the customers to foot the $2,800 bill for replacing the unit. If this same sort of thing happened with Genesis, for example, I think the solution would not be quite so easy. Earlier I mentioned write amplification, or in other words, how much data is actually written to the media. As an example, let's say I need to write 1K of user data. My device has a 2K block size, so the flash media will write the full 2K. A media write value of 2, an application write of 1, means a write amplification factor of 2. Of course, in reality, the file system needs to update the metadata for that file, which is another small write to a different 2K block. So for my 1K of user data, the real factor is probably closer to 4. The larger the write amplification factor, the more writes to the media, and the faster we wear out the flash. This can be one factor in critical system failures and sluggish performance, although both are use case dependent. Studies of Android were performed in both phone and automotive environments. These studies showed write amplification factors ranging from 20 to over 100. Some of this comes from the file system, some from the block device, and some from choices made to ensure data integrity. If an application vendor reports that their app will write roughly 1 megabyte per hour worth of log files and updates, that actually could be 100 megabytes per hour at the level of the media. This sort of write load comes back to that Tesla use case and is something the system designers really need to plan for. Speaking of data integrity, the impact of sudden power loss can be felt at boot time. In many cases, boot time is regulated. File systems organize the data they must read at mount time and, of course, repair possible damage that occurred when the power was unexpectedly lost. Here, a journaling file system is compared to a solution with a delayed background correction. Our test showed that this mount time could spike as high as 1.6 seconds. If the requirement for the entire system startup is under 2 seconds, it's really pretty unacceptable for the file system to take up 3/4 of that time for repair. A final impact of lifetime is fragmentation. Even if the individual blocks shown here are the proper size for the flash media write, the system shown on the right requires more system metadata for the stored files. And the erased files leave holes which are slower to fill. This is a curious side effect of managed NAND flash, and we can demonstrate that by measuring the throughput. While a less fragmented file system continues to show good throughput, the fragmented system gets worse over time. This graph shows the write performance, but we've also noted a significant drop in the read performance. These effects have been seen on mobile phones, which slow down over time. We measured the data written and saw the write amplification factor also grows over time on a fragmented file system. So what kind of impact will this have in an automotive environment? Performance and data integrity balance, everything I've been talking about here, that's the second challenge, really. I've shown how fragmentation and write amplification can both slow down the system over the time. In an automotive design, a performance drop of 20% could push things out of margin, causing a failure of the entire system. While this is less of a factor for IVI, in new designs with clusters handling everything, this could be a threat for a safety-critical system. Another noticeable impact is increased latency, the time an application must wait for the storage operation to complete. We've noticed in drone and camera designs that latency can result in frames being dropped. This is very relevant to dash cameras and to digital video recorders. What if the frame dropped is the one that shows the cause of the accident? So the final challenge, I'll just kind of catch all for other effects. Failsafe operation of the entire design is one. We focused on flash media and challenges here today, but the entire design needs to be examined, along with all of the failure cases. Some of this comes back to an over-the-air update, a time when fail safety is really paramount. One very public example, although the resolution has not been disclosed, was the FCA reboot in Uconnect. Instead of a design which returned to the last known good state, it continued to try the update, and upon failure, tried again. My understanding is that the head unit continued to provide power for these retries without the owner's knowledge, and vehicles parked underground or in a garage could run the battery dry with continual retries. Another problem that needs to be guarded against, and this is the biggest one in my opinion, is unknown future applications, especially in newer Android designs where an application could be installed by the user. I'm reminded of a bug in the desktop version of Spotify. In idle time, while not streaming, it would write quite a bit of data to the media, ranging from 10 to 700 gigabytes per hour. How would this sort of a bug impact an automotive situation? Well, not well. Can Android or the hypervisor detect this sort of out-of-bounds behavior and stop it somehow? Even worse, what if this sort of failure was triggered in the future by some sort of a cyber attack? So, in summary, the flash memory and the file system have a huge impact on the data integrity and lifetime, the performance, and the system integrity, also known as reliability or fail safety. For automotive, the newest use cases with mobile phone-like flexibility will only increase the challenges here. And remember, an automotive design needs a lifetime measured in several years instead of several months. I hope this brief talk has given some visibility into these data storage challenges. As a technical product manager, I've spoken to future customers with this sort of challenge frequently over the last few years. In our event space, there's also a white paper which goes into a lot more detail than I could have possibly done in the last 15 minutes. So I've got time for some questions and answers, though.
Thanks, Tom. And as a reminder for our audience, if you have questions for Tom, please feel free to pop those into the questions window as part of our discussion. I have a question for you to kick things off, Tom. As you're looking at data storage challenges in automotive, particularly this year and as we move into next year, how would you prioritize what those challenges are in terms of significance and what we need to be focusing on over the next 6 to 12 months and beyond?
Yeah, with the migration towards Android that we heard about in the last session and that we're definitely seeing, I think that, as I just pointed out, the number one has got to be guarding against the unknown future. We don't know what new apps are going to do. We really need to make sure the hypervisors or Android itself are tooled such that they could stop that sort of an overwrite situation. We don't want to go too deeply into that. That's probably number one. Really knowledge of the Flash and being able to respond to how the design has happened, like what Tesla ran into. That's probably number two right there, because Flash media continues to get smaller in terms of density, in terms of lifetime, and it's really something that needs to be managed now, not 8 years down the road. You want repeat customers. Especially these automotive tier ones want repeat customers. They want people to continue to buy their car, not to move on because of a bad experience 8 years down.
And another question, thanks, Tom. Another one, how should I estimate the lifetime for a memory component?
Well, so the first place to start is by having a conversation with your vendor. Really understand what they're giving you. The data sheets will say things like it's got a 4,000 write and erase cycle lifetime. But have that conversation with the vendor, because, as I pointed out on the write application slide, there are three different factors: the file system, the media itself, and then the application. So understanding what the block device does for reliability, how it writes, that's really key. One way to deal with that is Tuxera, for instance, has a flash testing service. So we'll take your design and we can run those tests and get some of that advanced lifetime information. And we can also help you set them up to run them yourself.
And as you look ahead toward 2021, where do you see the opportunities and challenges in this data storage market as we come out of this rather unorthodox year that we've been living in the last many months?
Yeah. Well, security is key. We're seeing more devices in locations that we weren't expecting to. The same thing as we're working from home instead of working from the office. I think security is definitely a direction we're headed. Have been for years, but I think there's more of a focus now, and that goes from the media all the way up.
It will continue to be the case as we advance our driving systems to autonomous and
exactly
electric and other modes moving forward.
Definitely.
Very good. Well, Tom, I want to thank you very much for the presentation. This was fantastic. If anybody has questions after, please feel free to connect with Tom for more details. But thank you so much.